Hello. Today we're going to do simplifying radicals. So radicals are the product of a rational number multiplied by itself and then under a square root. A perfect square is the product of a rational number and itself. Radicals are when those are under square roots. So you should know at least the first 10 perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. Some others that you might want to put away: 11 squared is 121, 12 squared is 144, 13 squared is 169, 15 squared is 225, 25 squared is 625. Perfect squares are what you can take a square root of and get whole numbers. So if you have the square root of 16, that's the square root of 4 squared, and so then you know it's 4. Like radicals are radicals that have the same root and the same number. So square root of 3 and 5 square root of 3 both have the same square root and both have the same radicand, the number underneath the square root. So square root of 3 and 5 square root of 3 would be like radicals. We do things with radicals. There are some properties. You need to know them going in both directions all the time. You can take a square root of two things multiplied together underneath and break the square root up into the two factors. You can take two square roots being multiplied together and multiply underneath of a single square root. So you got to be able to go in both directions. Huge on all of these properties. Quotients: if you have the square root of a fraction, you can break it up top and bottom. If you have the square root on top and bottom, you can put it together. Either way. When you're multiplying numbers in front and radicals, the numbers that are not underneath the radicals get multiplied together, and the numbers that are under the radicals get multiplied together under the radical. Rationalizing the denominator means you don't want square roots on the bottom of a fraction, and so you do that by multiplying the easy way. The square root over itself works fine for everything but numbers where you need a conjugate. You'll get to that in Algebra 2. And you can factor out, you can use the distributive property on radicals just like you can on anything else. If you have the square root of a number and it's the same across an addition, you can factor that square root out. So let's see some of these properties in use. When we go to simplest radical form, this is not decimal form, this is exact form, radical form. We're taking and using the property to break up our square root, saying 18 is the same as 9 times 2. So we can break up that square root into the square root of 9 times the square root of 2. Because the square root of 9 is the perfect square root of 3 squared, and the square root of 3 squared, the square root and the squared cancel each other out to just be 3 root 2. So we are looking for this 9. You're looking for the part that you're going to know reduces down to the number outside. Notice that underneath the radical, that part just stays the same. It is stuck as the square root of 2. You can't reduce the square root of 2. We don't know the square root of 2 is a decimal that never repeats and goes on forever. It's an irrational number. So it just stays the square root of 2 for the rest of the problem. So usually we don't have to go through all of that shown work. We can look at the square root of 54. 54 is 9 times 6. Square root of 9 we know is 3. So it's 3 root 6. We know that square root of 6 doesn't reduce any farther. 6 isn't one of our perfect squares, so we could break it down into the square root of 2 and the square root of 3, but we couldn't do anything with that, so then we'd have to multiply it back together to get the square root of 6 anyways. And so you just leave it. It's 3 square roots of 6. Rationalizing the denominator. You can't leave square roots on the bottom of the fraction. No radicals in the denominator. And so we're going to multiply by the square root of 2 over the square root of 2. So we're going to have multiplying fractions ain't no problem. Top times the top and bottom to the bottom. 3 root 2 over root 4. But the square root of 4 we know. This is why we did it. No square roots in the denominator. So if we use our trick again to get the square root out of the denominator, multiplying by the square root of 5 over the square root of 5, because square root of 5 over square root of 5 is 1. Anything times 1 is itself. So we're just changing the way it looks. We're not actually changing the number. But we're changing the way it looks so that we don't have a square root in the denominator. We have 10 root 5 over 5. Oh, and what's 10 over 5? 2 root 5. Sometimes you have to break the square root up first, so that then you can rationalize the denominator. Multiplying by 1 in the form of square root of 3 over square root of 3. We have the square root of 6 over the square root of 9. Square root of 9 we know is regular 3. No square root on the bottom of a fraction. Square root of 5 over square root of 7. Square root of 7 over square root of 7. 7 times 5 is 35. And the square root of 49 is, of course, regular 7. Rationalizing the square root, one of the ways you're going to have to work with fractions all year long. Chapters 11 and 12 at the very end of the year, we work a lot with square roots. We work a lot with fractions. So the people that haven't figured this out by that point have a really hard time at the end of the year when we've been doing this since the first week of school. This is something that we want to get down to make the end of school a lot easier for us. Combining like radicals. So just like x's, you have to have the same variable, the same power. Here you have to have the same square root with the same number underneath it. So if you have 2 root 3 plus the square root of 3, you have to know that that means that there's 1 root 3 there, so that you have 2 plus 1 root 3s, 3 root 3s. Usually we don't even bother to write the parentheses 2 plus 1 part. We just go, well, it's 2 plus 1, so 3 root 3. So in this next one, we're going to identify these two as our like radicals, same square root, square root of 5s. And so we're going to combine them. 4 plus 7, there are 11 root 5s, plus 1 root 2. You can't combine square roots that are different with a plus sign. We're going to write the small one first, and then the big one. Oh, I did a checkpoint for you up there on accident. Oh, I did a checkpoint up there for you on accident. So you guys get some free checkpoints being done for you. These 3 checkpoints I'm going to want you to do once we're done with this last example, and then check. So example 7, they don't always look alike even when they are alike. we can reduce the square root of 27. The square root of 27 is 9 times 3 is 27. So the square root of 9 is 3 root 3. So then that is a like radical with 1 root 3. And you can combine your like radicals. 1 plus 3 is 4 root 3. So you have 2 root 2 plus 4 root 3. Alright, so try these 3 checkpoints. Pause me. Try the checkpoints. And when you unpause, the answers will be there for you. So check your 3 checkpoints. I got 9 root 7, 5 root 2 plus root 11, and 11 root 2. Circle any ones you have questions with. Make sure you ask me those tomorrow. And I hope you had a great time. See you after the weekend.